Aaron was here doing mathematics when he got seduced into moving over to philosophy and persuaded him that he would take an interest in philosophy and logic and notions of human reasoning. And then that took him eventually via Edinburgh into artificial intelligence. So it's very good to have him here to give us a sort of different perspective on what's going on here. So a lot of the time we've been thinking here about working with symbolic representations and working with other sorts of representations. And we're talking about axiotizations. Where do we get these axiotizations from? We're refining specifications. Where do we get these ideas from? So there's things to be, things I think is helpful for us to think about, at least from time to time, about these more general issues that are happening. So very good to have you.
Well, thanks for giving me the opportunity. I need help. I'm working on problems that are basically too difficult for me. And so one of my hopes is that some younger, brighter people will see ways forward, whereas I tend to sort of go around in a slowly moving spiral. And just to put some scale on that, it was around, I did my DPhil trying to defend Kant's philosophy of mathematics, finished in 1962 in this university. Then in 1969, I was at Sussex University, a guy called Max Kluge, who works on vision, introduced me to AI, and I started learning to program and so on. And he pushed me much faster than I really wanted to go into AI. I ended up spending a year in Edinburgh in 1972 to 3, where I had my brain rewired, because I was meeting very bright AI people who were world leaders, and they were willing to talk to me, which was wonderful. Anyway, the idea that I got around that time was my defense of Kant's philosophy of mathematics was mostly based on a lot of examples, and I wasn't very satisfied with it. And so I thought maybe if I can show how to design a baby robot that grows up to make mathematical discoveries in the way that I think humans do, and more recently I think some other animals do that I don't know they do it, then maybe I can show in a way that Kant never could have why he was right in what he said. Anyway, that's the background to all of this, and I'll be going around in various kinds of circles, and it links up with developmental psychology and biological evolution and robotics. And maybe, above all, questions about what forms of representation are suitable and useful for the kinds of things that I'm talking about. And I think the ones that we now know how to put into our computers don't seem to do the things I'm talking about. But that may just be because I don't know enough about them. And by that I mean the ones we put in our computers, including neural nets, predicate calculus, all sorts of things that I know, which may not be everything there is. So, I have a very chaotic set of slides and some videos and demos and things, and I prefer not to have long discussions, but I certainly don't mind if someone's got questions or clarification in the future. And this is roughly what I've just said. And one of the key ideas is the idea of a toddler theorem. And by that I mean that I think very young children, humans, discover things that mostly go unnoticed. In fact, they don't know they're discovering them, but they use them. And they discover them through play and exploring the world around them. And initially they're picking up knowledge empirically, so they're learning that if you do this, and there's a thing on the table, the thing that was there in front of your hand moves. And if you bring your fingers together when there's something there, then you can move your fingers and the thing that was between your fingers moves too, and so on. And then later, this empirical knowledge gets reorganized, not just once, many times for different bits of knowledge, into something like a theory that's deductive. So kids discover that instead of doing everything by trial and error, you can work try some things out instead. Now, the importance of that was evident to a guy called Kenneth Craik. I don't know if any of you know of his work. He did work in mathematics and logic. He wrote a book around 1947 or something. He unfortunately got killed riding his bicycle, probably in Cambridge, as a young man. But one of his ideas was that if animals can develop working models of things in the environment, then instead of having to try things out that might be dangerous or whatever, they can try them out in their models and realize they're going to get hurt instead of actually being hurt. And you can see how that might be useful biologically. Anyway, I think he was basically right. The problem is, what are the forms of those models, and what are the kinds of things that humans can do with them, and what other kinds are there? So, for example, one or two of you may know my colleague at Birmingham, Manfred Kerber, who once told me about his daughter, who got a great delight from shutting any drawer that she saw was open. But at first, she shut the drawers like this. And that was very painful. Put her hands over the top of the drawer and push. But after a while, she realized, you shouldn't do that, you should do that. So that's an example of a toddler theorem, which, having discovered on some drawers, she could probably then use on lots of others of different heights and colors and sizes and so on. She probably, in fact for certain at that age, could not say, this is what you should not do and this is why. So it's a kind of reworking of the system. Now you may know that something similar is very common in children learning to speak. They first learn to speak by listening and repeating, and they store patterns of words that can be assembled in various ways, and become quite fluent. And then, I think starting in the third year, it varies, children don't all develop the same way, they switch to using something more like a generative grammar, and then they abandon some of the things they previously learned, and instead use this deductive system, the grammar, and say things like, Johnny hit at me, I sitted on the chair, I ran home, whereas previously they would say, Johnny hit me, I sat on the chair, I ran home. Because what they've learned are rules for forming the past tense, and those are just some examples, and they do this lots of things. Later, and then when they're at that stage, nothing you can say to them without making mistakes makes any difference. They will still get things wrong. But later, they correct spontaneously, and they can deal with the verbs that don't fit the rules. And I think what's going on, this is sometimes referred to as U-shaped development, so they become quite competent, then they become relatively incompetent when they've switched over to this new form of words, although deep down they're much more competent because they've got something with much greater generative power, but the surface behavior suggests a kind of forgetting what they already knew. And then later they become competent handling the rules and the exceptions. And if you think about it, if something starts off learning usable patterns for communication and then reorganizes it by producing a generative grammar with appropriate mechanisms and rules and whatever, adding the ability to deal with counterexamples is a non-trivial extension to a system that can handle a formal grammar or derive theorems. I guess most of you have not had to deal with theorem provers that have to handle exceptions because your systems don't have exceptions. So the question doesn't arise. But if you had to handle exceptions, then maybe you'd have this problem. Well, maybe Lakatosh would say they do have exceptions. So that's another issue. Okay, so here are some things. Let me just show you one to illustrate the spoon. I've got various videos, and they could take too long, but I'll choose a few random. Here's a child aged about 11 months, I think. So he's, as you can probably see, someone's holding a top of yogurt on the floor, and he sometimes feeds himself, as he did there. He sometimes does experiments. again trying to, it looks as if he's trying to transfer the yogurt to another experiment. That time it's set up. Here you go. Morphine of his belly. He notices some on the floor, tries to pick it up, puts it on the spoon, where it belongs, and then transfers it. He seems to have got some kind of theorem about transferring food in a spoon to your mouth, but he's trying to apply that theorem to transferring food to a carpet, I think, and it's failing, because he hasn't realized the differences between the carpet and the mouth. That's my interpretation of what's going on. And he does another little experiment, doesn't finish it. And he ends with a rather complicated thing, which I think is coming soon, where he decides to transfer the spoon to the other hand. It's as if every time he's putting the spoon in, which is presumably primarily to get the yogurt out, he has the idea of trying something different, which is letting go of the spoon, it seems. Now, he transfers the end of the spoon, and it's quite a complicated operation. You can try it yourself, holding something like that, and then getting that end into the other hand. You've got to, and he succeeded. Now, I do not believe he had any awareness that he was dividing up his life into these various experiments. I don't think he had any explicit goals for doing them. I think he's programmed genetically to respond to situations, not by behaviors, but by goals being created. And when those goals are created, depending on what else is going on, some of them will take control and drive the behavior, not directly, there may be some kind of backward derivation of what to do to achieve that goal. But sometimes it may just be, try this or try that. And one of the ideas I want to get across is that the child, like the rest of us, is confronted with a rich and very richly connected environment. It's richly connected in that there's all this space and all the things are in the same space at the same time. But also there are lots of different kinds of things that can be brought into contact with one another. They can be used to operate on one another and so on. There's an awful lot of stuff there. But it looks as if part of what the child is programmed to do is to divide it up. And one way you can divide up this world into subworlds is to try certain things and see what happens if you try those things, and then try minor variations of those things. So that way you're focusing on a small subset of the properties of this world. That idea is a very important theme in a book by Annette Karmiloff-Smith. Has anyone come across her work? She was one of Piaget's, I don't know if the word is disciple, because he now disagrees with it, but she worked with Piaget in Geneva on the genetic epistemology project. And they have different ideas about things, but I've been reading, in addition to her book, Beyond Modularity, dated 1992, which I should have read long ago, but didn't, because I read summaries and thought I knew what was in it. But when I actually started reading it a few weeks ago, I found it was much deeper and richer than I had thought. I also discovered through her, because I wrote her about a different topic, and she told me that Piaget had written something about necessity late in life. And I went to Amazon and found he'd written two books, one on possibility and one on necessity. So I've started reading those as well. And I'm going to try to show you connections between some of the things that I think Piaget was getting at, and some of the things Karmiloff-Smith was getting at, and my old problem of how to show that Kant is right about the nature of mathematics, and the newer problem of how to make a robot that learns in something like the way we do. And I've already told you quite a bit about it. In fact, if I stopped now, I expect quite a lot of you will be able to go away and continue developing not toddler theorems, but theorem prover theorems, or some researcher theorems. Okay, Karmiloff-Smith had the idea that whereas there are some people, like Mr. Spelke, who you may or may not come across, who think that there are some things that are innate in children, and if you do lots of clever experiments, you can find out that they have a concept of an object, or they know something about continued existence or an out of sight or whatever. Karmiloff-Smith's notion is that what the genome provides, and this is also the idea I've been working with for some time, is not specific knowledge in the case of humans, but very specific ways of finding out about a world of the kind we live in. So it's specific in that it's not totally general learning mechanism, which some people in AI are trying to develop based on ideas like compression. So if you use algorithmic complexity, you can say that or ideas related to that, you can say you just try to find ways of collecting lots and lots of data through your sensors, and maybe sensors and motor signals, store the information, and try to find the best way to compress all that information, and then you'll learn everything there is to be learned. And as far as without having any prior assumptions about the world, and as far as I know, there's only one kind of learning mechanism that really does learn substantive amounts of stuff without any prior information, and that's biological evolution. But it takes a few billion years and quite a big planet, and lots of things being developed in parallel to provide mutual constraints and so on to drive that process. Whereas young children are learning all sorts of things much faster than that. Now, we know that biological evolution can produce highly specific, highly competent mechanisms at birth or at hatching. A newborn chick, for instance, or a duckling. It finds its own way out of the egg, no midwife needed. Where it's ready, it picks its way through and comes out. Looks around for the mother and starts following the mother, but it can also pick for food. Mother hens do not feed their babies, nor do mother ducklings. They may lead them to where the food is, but they don't say, yeah, you eat this, or pick it up and drop it in the mouth, the way other birds do. A newborn horse, or most grazing mammals, within minutes of being born, will be able to get up on their feet, look around, see where the mother is, go for the nipple, and start sucking. Maybe, if not exactly minutes, within the first few hours. And some of them can even run with the herd, wildebeest, can run with the herd, definitely within minutes. Why? Because the mothers can't pick them up and carry them. And why do they need to run? Because there are lions and other things trying to eat them. It seems evolution found ways of building them very competent in the womb. Now that proves evolution can produce very high levels of competence, things that no robot can do. I mean, the things that a newborn wildebeest can do are not matched by any existing robot. But there are also probably limitations. I have no idea how much these animals know about what they're doing. They can do it, but do they know what they're doing? Do they know why they're doing it? I suspect not. I'll come back to that. So, evolution could have made us, and young lions and young crows, like the young deer, but didn't. But that doesn't mean evolution made us empty of all knowledge with just some totally general learning mechanism. There's something in there which is geared to learning about things in space and time. Exactly what is what I don't know, but I think one of its features is that it divides up the world. It doesn't just try to learn about the whole world all in one, as if it's all one thing to be compressed into summaries of your sensory motor inputs and outputs. And there's something about the way the behavior is structured that brings about the division of the world. Of course, at a later stage, this may be done by parents. They'll provide particular toys, and different sorts of toys will encourage kids to go through a collection of related behaviors appropriate to those toys. So the idea that Karmiloff-Smith had, which seems to be roughly right, is that young humans, and I think also quite a number of other species, although I don't know quite how many, can explore a bit of the world, can collect information empirically, and then can reorganize it so that they can use what they've learned to deal with new situations by working out what needs to be done. There was a spectacular example of this that became very famous in 2002. If I say Betty, the hook-making crow, how many of you have heard of that? Okay, not everybody, so I better show a video. This was a New Caledonian crow, kind of crow from New Caledonian Islands somewhere near New Zealand. and they're particularly intelligent, but all corvids are, as I discovered when I was sat in a garden watching magpies building a nest in the tree in the next garden. What am I doing now? It's another spot. I could have done this preparation better. And I saw the magpie flying up to where the nest was, holding a twig across in its beak. And when it approached the nest, it got stuck because there were two branches coming up in its way and couldn't go through. So it went around to the side and seemed to be pushing it sideways. I couldn't see exactly what was going on, and then it let go and came back to where it wanted to go the first time and continued. And then I started thinking, would I be able to make a nest that was rigid if I had one hand, they have a beak. They can do things with their feet, but I don't think they're doing making nests. Would I be able to, or would any of you be able to make a rigid nest by going out, fetching one twig at a time, and bringing it up into a tree with a place with a couple of branches? Think about how you'd get a rigid structure. Initially, there's no way you could join them up. Anyway, they do. They don't always work. Sometimes they lose their eggs, but mostly they work. Anyway, this was Betty. You can just about see she's got a straight piece of wire trying to get a bucket with some food in it, and failing. Occasionally, she managed to get it out by pushing the wire through the handle and then pressing against the opposite side and came out. But instead, she stops, sticks the end of the wire into the ducting tack that's holding the tube in place, expertly moves the other end round, checks that she's got a hook, and then shuts it down. And it seems there that she knew exactly what she was doing. There was no trial and error. In fact, trial and error would not bring about that solution in a million years. It was totally random. That was the 7th hook she'd made. They were originally not planning to see if she could make hooks, but to see if these, there were two of them, a male and female, if they could recognize a hook as a solution to the problem. So human had made hook, made a wire, left it there, given them the problem, and both the male and the female very quickly saw that they could get the food out. And then on one occasion, the male flew away with the hook, and the female came, no hook, but she saw a straight piece of wire, so she tried to get food out. On that occasion, after failing, she stuck the end of the wire in a crack. There was a tray at the bottom, a plastic tray. She stuck the end of the crack and bent it. And she didn't get a very good hook, but it was curved like that, and it was adequate. She managed to get food out. And the experimenters were amazed. They thought, this is not supposed to happen. They don't know anything about wire. These birds evolved with trees and leaves and twigs and so on. Wire is a very different material from anything in their natural environment. So they took that away and tried again. And apparently 9 times out of 10 she made a hook, and I think the extra one, I asked Jackie Chapel, who was one of the team, she said on that occasion she managed to get it out without bending the hook. Now, trial 7 was that one. There are videos on the Oxford Ecology Lab's website. Betty died a few years ago, so you can't read her, but the videos there. And she makes hooks in several ways. I've described 2. Another one she made by flying up to a little perch on the wall, something sticking out of the wall, and there's a hole next to it. So she perched on this dowel or whatever it was, stuck the wire in the hole, and bent it around and came back. Another one, she flew up to a rail, which is not very clear in the video, but it looks as if what she's doing is flying up to this rail, and then with the wire, straight wire in her beak, she bends down, and then with her foot holds the wire in place, which she wouldn't be able to do on a flat surface, which is presumably why she flew up to the rail. So she holds the wire and then pulls the end up with the beak and goes back and gets it. And all very, no messing around, trying, flailing about, just very purposive. So it looks as if she, in some sense, understands what to do in that micro domain for getting food with a piece of wire on. Whether she knows she does it, whether she knows anything about how she's learning is a separate question. And Karmiloff-Smith theory, partly backed up by evidence, is that children go through a variety of stages. In the first stage, they have the behavioral mastery because they've learned lots of special cases. Then there's a stage where they start reorganizing that, and that it becomes more general. They can cope with new situations they haven't learned about, and they may not be totally reliable. But nevertheless, they do significantly more at that stage. And that's like the children who started learning grammar to replace the learned sequences of example of words that they know how to use, but they start getting things wrong. Her next stage is that the learner becomes aware that something's going on here that was different and can think about it and use it. And you can check that with children by asking them what would happen if, or trying to get them to do something which is going to have a silly consequence or whatever, and they seem to be able to reason about it. They can think about that, as opposed to just using knowledge in achieving their goals. And at a later stage, they can think about it, reason about it, talk about it, and you can subdivide it and say there's also a possibility of thinking about other people doing the same thing. And that's been absolutely crucial for humans, because you can see when other people are trying to learn something that you've already mastered, and seeing when they've got bugs in their attempts and there's something wrong, and you can help them in various ways. Not necessarily by telling them the answer, but giving hints or changing the problem or whatever. And that's why humans do not all have to go through the same learning process as all their ancestors to get to the same end. And that's been absolutely crucial difference between humans and other species. I suspect we may be reaching the end of a phase in which it's always possible for bright people to learn everything they need to know in order to come up with yet another great new idea. Maybe it's not possible anymore, I don't know. If it's, I invented a silly label for that, the singularity of cognitive catch-up. If we're there, then maybe we'll need computers to help. Or maybe there's always another level of complexity where things become simple and you don't have to read all the previous stuff in those places. I don't know. Okay, so I've tried to give you examples of what could be meant by saying that a learner carves up this rich reality that it's embedded into sub-realities by developing specialized skills, partly by doing specialized things in the world. And some of them may be using specialized bits of equipment provided by parents or just by the environment. There might be sand, or there might be mud, or there might be stones and things. I have a specialized bit of equipment which is in this one. Okay, well, it doesn't matter, I'll just tell you. This is a child aged about 12, somewhere between 11 and 12 months, standing on a piano stool, or sometimes standing, sometimes sitting. That's another subdomain. You can get up and get down and do things with your legs and so on. And it changes things, it changes what you can reach. So there's a bunch of toddler theorems to do with the consequences of sitting up and sitting down, whether you're on the floor or on a chair. Anyway, with a piano, in the video, the lid's open, so the keys are accessible. There's a typical music holder hanging down, and this child tries things, sometimes with just one hand, sometimes separate fingers, sometimes the whole hand. And every now and again he tries something different, like grabbing the music holder and doing this, and so you get a different bit of the world that you can experiment with. Just before the video ended, he had learned he could do something like that at a and for some reason moved over higher up the piano, higher up in pitch, moved around, and did the same sort of movement. And I have no idea what would have happened because I wasn't there taking the video, just ended there arbitrarily, maybe ran out of memory of the camera or something. So in that little episode, you see the carving up of the world of opportunities into sub-things, and he is alternating between them. using fingers on the keys. Oh, in one case, he slides the finger back and forth on the key, tries to see if he can press it, and obviously finds it a bit harder to press at the far end where it goes, and with a different mechanical advantage. So, one of the subworlds is a link between actions and sounds. And there are different kinds of cases. There's this kind of case, and this kind of case, and this kind of case, producing different things. Now, in order to get the kinds of generalisations that Karmiloff-Smith talks about, and which I introduced in connection with the language example, where you reorganise the information, you have to have reduced the relevant bit of the world to something fairly simple, otherwise it's going to be very difficult, especially for a toddler, to develop a theory. So there's obviously some research to be done on what opportunities there are for carving out subdomains within which it's possible to come up with a good theory. This requires a number of things which will be related. One is coming up with a formalism to represent the information. I hinted that I don't think currently available formalisms used in computers, theorem proving and so on, are adequate to task, and I may return to that. You also need an ontology. You need to have a way of categorizing things in the world, and that's not just types of object, but also types of process, types of relationship. I don't need to say that to an audience like this. Types of causal relationship. There are some people who don't think in terms of categories of objects when they ask what is a child learns. Even some people who work on machine vision think that the whole task of vision is to find objects and label them. Totally daft. It's not what vision is. Anyone who does mathematics uses vision for all sorts of things. So you need a form of representation, you need an ontology, and of course that needs to be represented somehow. So the division between form of representation and ontology is a subtle one. How do you get the semantics into the system? And I think it's got something to do with the sensory motor connections with the world, but not in any simple way, for reasons that I'll come back to. You need a deductive mechanism. You need a mechanism of inference which enables hypothetical or an actual situation to be thought about in terms of a hypothetical change. So if I pushed this in that way, what would happen? If I stuck that in there and did that, what would happen? And that requires algorithms for the forms of representation, for operating on the forms of representation to see what follows. You also need an architecture which can combine that with your perceptual apparatus, your motivational apparatus, and your planning apparatus, and your plan execution apparatus, so that you can actually use the results of your theorem proving in solving practical problems, as Betty clearly did. I'll show you, Josh, the little boy failing. If I can find it, to type the right thing. I had a different way of doing this, and I thought I developed a better one, but obviously it's not so good. Okay, playing with a toy train made of trucks. And he's picked up one of those loose and he wants to join around. So he shakes off the one that's already joined. And he's looking at these two. He sees that one's blank on one side, so he puts it down, picks it up so that he can see the non-blank side, and he's got holding the other one. And now he's trying to join the two rings, completely ignoring the hook over there. He's getting cross. Getting very cross. Tries again, gives up, and it's quite clear that he's highly competent at manipulating things. For instance, he picks up that rock, he picks up something else, sticks it in his mouth, he looks around, he sees a crack in a chair, he goes and sticks that little peg in there. So there's a huge amount of toddler competence about many toddler theorem. By the way, one of the things he did was, you probably didn't notice, he was crouching, and as he was picking up one of the objects, he also sat down. So he moved sideways and sat down without losing his balance or anything. So that's quite competent, but he just didn't understand that you can't join two rings at that stage. I saw that video a few weeks after it had been taken. I asked his father to watch out for the transition to when he worked out that you have to have a hook and a ring. You can't just join two rings. And he didn't know what I was talking about because he already knew how to use the hooks and the rings to join the train. So something had changed without anybody seeing it happen. So we missed a great opportunity to see a child debugging its theory of that bit of the world. If any of you have children, remember all this and keep your eyes open, because I think there are lots and lots of things going on that mostly don't get noticed. Here are some examples of toddler theorems. I mentioned some. Pushing a long rigid object makes a foreign move. Pulling an elastic string makes a foreign move. Rotating a rigid object held on one end makes a foreign move, but in a different way from pushing or pulling. But if you're holding and rotating, you get small motion where you're holding, big motion where you're rotating. And these things are obviously fun. And I've given you this one about the spoon containing stuff horizontally, makes the stuff move. There are other things that you can do with counting. When a child learns to count, I remember one of our kids, I asked him to count my fingers, and he did, and gave me the answer. He was humouring me, and then I said, what happens if you count them the other way? I said, I don't know. Try it. And he counted them the other way. I said, oh, it's the same. It was a delightful piece of empirical discovery. Later, at that stage, I wasn't doing this sort of stuff systematically, lucky for him. Later, I'm sure that if I'd tried the same thing, he would have treated me as completely stupid, because he'd have reorganized his knowledge in such a way as to realize you don't have to count it the other way. But how many of you could give a proof that it doesn't matter in what order you count objects, you'll always got to get the same thing? It's probably fairly obvious. It's a theorem about one-to-one correspondences. But here's one that's maybe a little more fun. I don't know of anybody else who's talked about this, if I can find it. Oh, it's on the right. If you give a kid lots of blocks, and I assume they're in different colors, the child might discover this, but I don't know of any child who did discover this, but if they did, it would be an example of another domain. If they've got this collection of blocks, they might discover they can arrange them into a collection of rows and columns, like that. So you take the first three over there, the next three over there, the next three. So you can get from that to that. If you take this lot, you can rearrange them and you get these two rows, which are the same length from the three. But I've just added one more block from there to get that. Take my word for it. And then I added one more and I got that. There's no way you can rearrange that one to be anything but a single row. So what would have to be in a child to make it, enable it to discover that and then start thinking about why not? And could a child playing with that convince itself that it wasn't just that it hadn't tried hard enough, or that it wasn't that these blocks are the wrong color? Because when you're learning about these things, you're learning what matters and what doesn't. And clearly when you think about how you can rearrange these, presumably they're all in cubes, your ability to rearrange them has nothing to do with their color. And that's learning something about the decomposition of constraints in the world. Okay. So I'll leave that as something for you to think about. Could a baby robot play with this sort of thing and make these discoveries and then try to convince itself that it's not just an accident that it's failed to find a rectangle made of these, and it's not just an accident that it can't get 3 by something out of this lot, and it's not just an accident that it can't get 2 by something out of that lot. Well, that might be a new route to the fundamental theorem of arithmetic, the unique factorization theorem and the discovery of prime numbers. But as far as I know, it's never happened that way. But maybe it did, and it just wasn't recorded, because potentially, I think, the apparatus is there in the learning child, given the right environment. So there's another experiment, if and when you have children one day. see if you can guide him down this route and tell me what happens. Okay, so I'm trying to illustrate the fact that the world has lots of subdomains that can be explored. Some of them are sort of natural consequences of the nature of the environment, what it's made of, like the difference between a rigid piece of wood and a piece of string, which is flexible but not elastic, so it's got a maximum length and so on, and the things you can learn about that. But there are others which depend on ways we decide to think about the world. So for example, I can take a sheet of paper and I can draw some squares on it. And then I can ask questions about, if you put some coins on these squares and you'd like to move them diagonally, is it possible to get a coin from here to there? Subject to that rule that you can only move it diagonally. And I'll again leave it to you to think about that. There are things you can learn about what patterns you can make if you have coins on squares, depending on whether you're allowed to, or what patterns you can change, transform, depending on what rules you adopt as to how you can move them. If you can move them only horizontally and vertically, it's different from being able to move only diagonally. Which one gives you more possibilities? Is it obvious? Okay, think a bit longer, and you discover a toddler theorem, which as far as I know, most toddlers don't discover, but I suspect it's not beyond the powers of a 4 or 5-year-old. But you first have to get the question. So, what constrains you more? Being able to move only on diagonals or being able to move horizontally and vertically if you've got coins on a regular array? Now, there's a huge amount of stuff here. I've claimed that this isn't just humans. Has anyone heard of Porsche spider? It's a spider. I'm going to put these slides on my website, and there'll be a link to it to report on this. Porsche is a spider that eats other spiders, and it catches them in one of two ways. It can go to the edge of the web of the prey spider and pretend to be a fly caught in the web, and then the other one will come running to have its lunch, and instead it gets eaten by Porsche. But sometimes it doesn't work, and to cut a long story short, Porsche then just sits and looks around and thinks, and seems to be able, in some circumstances, to find a route to a place above that spider that wasn't tempted. And Porsche goes up around that route until it's about, and then drops down on the other one and eats it. Now, some scientists wondered how that was done and what was going on, and they did some experiments where they put some prey or food on a platform, and they built artificial little tree structures. And they found that Porsche it might take 20 minutes of sitting and looking, but it would then apparently work out a route, and then go down and long enough, and even while it's not able to see the prey anymore, and can't smell it because it's covered in foil, it would choose the appropriate route where there are forks. And one might be going in the right direction, but is not the right one because it doesn't go far enough. Another one may go that way and then come around, and it'll choose the right one. So it's as if it can sit there, staring, and computing a path, memorize it, and then follow it. But I don't know of any other non-human animal that's clearly able to do something like that. So it seems to be a very highly specialized competence. On the other hand, young children seem to be able to develop that over time, and one of the ways they can develop it is by playing board games, where it's helpful to be able to think several moves ahead. Save the patient. So what's common to all these things, the spider, the crows, orangutans, and humans, I claim, is that they all evolved in an environment containing 3D structures, processes, kinds of stuff, causal relations, and the possibility of partitioning the space into subdomains. Now, what that means is that if you were going to try to build intelligent human-like robots, we have to think about what that process of partitioning is like, what kinds of mechanisms you need to do it, and also all the other stuff about forms of representation, forms of reasoning, architectures, and so on. Whereas what most roboticists, in my experience, do is very different. They assume it's obvious what an intelligent robot needs to do. It's going to learn statistical correlations between its inputs and outputs or something like that. Or it's going to be trained and shown this is a cup, this is a boot, this is a spoon, or whatever. And maybe given some examples of things that it has to do, and then it will do that. And you can get somewhere with that. In fact, with some kinds of explicit programming, you can do very impressive things. Have any of you seen Big Dog, the Boston Dynamics robot? And you want to, oh, if you haven't seen Big Dog, you have to see Big Dog. Where's Big Dog? That's a robot. It's not two people dressed as a toddler. It's got a lawnmower motor or a couple, and it's got I don't know how many sensors and motors or motor connections, and it can keep its balance and keep moving in a wide variety of terrains. Don't let it go for very long because it takes too long. But you can give it a kick, and it'll detect that it's falling and stick out a leg. Okay. So that's it's able to recover. So maybe it's got a gyroscope or I don't know what, but it's got a lot of sensors, and it can also walk over very rough, climb over rough terrain or climb over boxes and things. That's ice, I think. Anyway, you get the idea. It's called a Big Dog, and the company's Boston Dynamics. You can't see it on the screen. You can find things on YouTube, or if you just go to the company website, you see Boston Dynamics. And one of the things I'll say about that is that it seems to be describable as having a high level of competence, which is the first stage that Karmiloff-Smith talks about, but it never can get to the point of reorganizing its competence. As far as I know, it's either programmed or trained to cope with a wide variety of situations, but it may have some generality. For instance, there's a neural net involved, which enables it to detect that it's approaching, say, the boundary of an envelope that it should be within, and then switches on compensatory mechanisms. But I don't think it knows in advance what it's going to do. And when it's finished doing something, I don't think it knows what it did. I don't think it knows what it didn't do. And it doesn't know why it didn't do it or why it did do what it did do. Whereas, although young children may start like that, they're gradually developing the ontology, the forms of representation, the algorithms that enable them to think ahead. As the child trying to join the train was doing, when he picked up, he shook a bit off in order to be able to put another piece in its place. That was thinking ahead. He was thinking ahead when he brought the two things together, but he didn't think ahead very well because he didn't understand the requirements for completing the job. At a later stage, he would presumably have understood why that failed, but at that stage, he just wasn't able to see why he had failed and just got frustrated. So, there's something about the evolutionary impact of living in an environment containing all these structured processes and causal relationships, which is capable of being carved out into relatively simple stuff, which can then be built on to get more and more complex competences. I think I'm already going too long, but I'll add a few more little bits about this. When you've learned about one domain, and you've learned about another domain, in many cases you can combine them because there's domains involving space and time. If you have stuff you can do with bricks, and stuff you can do with sand, then you put the bricks and the sand together and start seeing what you do with bricks and sand. Or you just other things you can do with water, you can pour it and stir it and drink it and whatever. Combine water and sand, and again you get a new domain which is composed of the others. Sometimes when you combine domains, the combination doesn't add any novel structure that you can't work out from what you had already learned from the two separately. In other cases, you do get new results. An extreme example is sugar and water. If you put the sugar in the water and keep stirring, magic happens. The sugar disappears. So you have to invent a notion of a kind of stuff that disappears in water, unlike sand, which you put in water and you stir it won't. So there are different kinds of compositions of domains. So all of this suggests that we need to look at the variety of ways in which new domains are constructed during development and education, and what mechanisms are required to enable that sort of composition to be done, and how you can learn, how you can tell whether what you've learned in these separate domains gives you all the knowledge you need. Often in mathematics, it does give you everything you need. You can just combine two operators and then don't get anything new. But sometimes you get infinite extra power, say, times you would expect it. Right. How shall I finish off this thing? John McCarthy wrote a paper, The World Design Chart. It was originally written in 1996, published in 2008 in the AI Journal. And he considers the common view amongst our researchers that if only they can find a way of giving a young robot, a new robot, a totally general learning mechanism and a large memory and sensors and motors, maybe a teacher, they'll be able to learn. In fact, Alan Turing suggested that in his 1950 paper. To my surprise, because I think he should have realized that couldn't work, but never mind. And John McCarthy reached the conclusion that evolution solved a different problem, and that historically there was no assumption. And I've tried to indicate that evolution solved many different kinds of problems. In some cases, lots of competences are there from the start. In other cases, meta-competences are there, which enable new competences to be acquired. And those meta-competences are various abstract qualities which I've begun to try to expose about how they are used, what they're used for, leaving open the question how they work, and that's where I need help with some of you, maybe in the next 20 years or so. Thank you very much. Objections?
More of a question actually. So you didn't mention analogy or like the taking of knowledge from one domain to another. It seems like there's quite a big role for that as well, right?
Yes, I think it's overrated as an explanation of what mathematicians do, but it is certainly something that's used a lot, and it can get you into a lot of trouble from one domain and use it in another. What I think is deeper and is more characteristic of mathematicians is discovering when you come to a new domain that you don't need to learn about it all over again because it's got the same properties as a domain you had before. But you don't deal with that by constantly remembering your first domain, and every time you're trying to solve a problem in your new domain, think back to the old domain, and then that's how metaphorical reasoning works. Instead, you realize that what your previous theory was not expressed in enough generality. You abstract, you leave out some of the details of the original theory. You now have a new theory, and it applies equally to the old and the new. And when you apply it, you don't have to remember its history at all. So that's a kind of subtle difference, but I think it gives much more power than always having to find an example from the previous domain to solve a problem in the new domain. But it's true that you often get ideas by the analogy. And if anybody hasn't read Polyo's little book, How to Solve It, it's a great read. It's quite small, and I must go back to it and see how much of it looks different in the light of the things I've been talking about today. But it could be that I'll find out he thought about all this. Nothing new to him. I just didn't see it when I read the book 20 years ago.
Do you have any idea what the different sort of representations are that we should be looking for? Or is that not quite the right question?
I have some ideas about constraints on the representations. For example, most people working in robotics, there may be some exceptions, but the ones I interact with, assume that a robot's going to have perceptual systems that take in information about the world and, as far as possible, try to encode the information using a global coordinate system. It might use different ones at different times. So when you go to a new room, it might set up a new set of axes or something. And that means it makes sense to ask how far away every object is from the robot, what the lengths of all the objects are, what the angles are at which the surfaces meet, what the curvatures are, and so on. And then they have the problem that they can't get that information because the sensors are noisy or unreliable. So they start working with probability distributions over these values in millimeters or angles or degrees or whatever. And I can't believe that's what I ever do, or maybe for some very specialized competency, or that newborn babies are doing things like that. So what's the alternative? I think there is an alternative which depends on the ability to, I talked to some of you about this earlier, to perceive partial orderings. A rich connection of partial orderings. For instance, if I look around the room, I can see all kinds of things that are nearer or further to me. I can see gaps between people, and some gaps are smaller than other gaps, and others bigger. So there's a small gap there, a slightly big gap here, a slightly bigger gap there. If you ask me to say, for instance, whether the gap there would fit 2 or 3 times into the gap over there, I may be able to say I'm not sure, but at least 2, maybe not 3, definitely not 4, or whatever. So you have a whole collection of partial orderings on which you can impose what I don't know if there's a technical term for this, but I call it a semi-metrical, transform it into a semi-metrical space. So I can say this is further than that by an amount that's at least 3 steps or 3 lots of these, but not more than 5. I don't know exactly where. And likewise, you can compare angles. I can say that the angle between here and that doorway is definitely, for me, is definitely smaller than the angle of this desk. And if this were an opening, that an opening, I might or might not be able to tell whether one of them is bigger than the other or not. I can just say things about the angle. But I can use the facts about the angles to tell whether I'm moving in the right direction when I want to go through the door. Is the angle getting bigger in the right way? Is it staying in the same part of my field of view? Is one of the edges of the door coming towards the line of sight ahead of me? If so, I should steer a bit away from it, and so on. So there are lots of ways in which you can collect this information, which is, from a certain point of view, fragmentary, as opposed to the nicely integrated collection of vectors in a coordinate system that other people are trying to get. But it's at least accessible. And also, it doesn't have to be, the lack of precision doesn't matter so much. You can use the ordering to say, I'm too near, I'm too close. You do need much more precision to be able to throw something up and catch it, or to crumple paper and throw it into wet a bit. But those are special cases, and exactly how that's handled, I don't know, but it may use some extra mechanisms which are not required for seeing the structural relationships that you can use to get the qualitative decisions about the opportunities and constraints. So if someone knows of branch mathematics or some computing system that can take in large collections of partial orderings with this extra slightly metrical extension, so you can sometimes not just say this is more, but something about how much it's more by ordering the differences as well as the things that you start with. Then maybe we can try and experiment on building a robot that uses a lot of that stuff. And then, of course, there'll be lots of questions about how do you get the generalizations that I've been talking about. How do you reorganize the empirical discoveries so that you get a deductive system? Am I talking about something familiar to anybody? Have you read about? Okay. If it sounds like absolute rubbish, tell me. Don't be shy.
I've seen something in a totally unrelated area that sounds a bit like that, and that's in these kind of first attempts at getting like theories of quantum gravity, where you're trying to kind of derive some notions of space and time, but you don't really have a fixed sort of causal structure, but you might have certain things to say, well, this is situated such that it could have caused this to happen.
So that gives you a kind of spatial ordering of this could have caused that, but not that, so you get...
Yeah.
Yeah, because what distance means just around the Big Bang is obscure.
Often you don't get partial orderings in that case, which is, I think, the odd thing, because you're talking about a geometric thing that's not transitive. So.
Containment would be transitive in the spaces that I'm talking about. But I don't know if that contradicts what you were saying. Anyway. Well, if anyone comes up with some good ideas about how to do it, and how to do it on a computer, I'd like to hear. Because one of the horrible thoughts is maybe biological evolution has done more things with brains than we'd even dreamed of in order to provide these abilities to reason about spatial structures in close proximity with things, properties like rigidity, impenetrability, and so on.
So one of the things that some of us have been working on the past few years is in exploring a mathematical domain, trying to decide which new bits of information should be stored for further use and which should be just thrown away. So have you looked at any of that in the context of infants or animals or such? Presume, you know, that there are lots of things that are going on, and each of these beings decides, okay, I keep this bit and I throw some bit away, or
Right.
does that or do they just retain everything?
I don't think they retain everything. There's some sort of attention mechanism selecting what to think about, what to perceive. But it doesn't have to just choose one problem and stick with it. Because what struck me about some of the videos I've shown you and some I didn't show you was how a young child seems to alternate between different experiments. And the yogurt one makes it very clear. There's getting the food, there's putting the spoon, and then go and see what happens. There's transferring stuff. And then right at the end, there's transferring this handle from one handle. Why? I don't know. So, it may be that during each phase of such a multi-branch exploration, the child switches between storing different things and keeping them separately. It hadn't occurred to me before that that could be a problem, but if it doesn't do that, it's going to be much harder later to find important generalisations. That's a good point.
Thank you very much.
I will put my slides on the web, and my talks directory, and the videos are all there, including the ones I didn't show you, with links. There's a wonderful one of an orangutan mother and child, which I can't make available, but you just see them doing little experiments, and one of them, the mother gets to the end of a beam and then does this, obviously testing compliance. And this is connected with the fact that they do a lot of foraging and go from one tree to another, and especially in Borneo, they can't go down along and up because it uses up a lot more energy than going horizontally. And also tigers like to eat things like that. But they can't go horizontally like the smaller monkeys and chimps because they're too heavy, the branches will sag. So they found other ways of doing it, like Tarzan. If they see a hanging vine, they can swing on it. But they can also go up that way on a compliant support and then make it swing until they can reach over to something else that's sticking up from the other tree, which is interesting. Talking to biologists want to learn that.